Okay, so okay. So if you guys saw this in class, you saw that you had, I'm going to use this as a black line. There was over here we had this idea of mole fraction of something. Oh, you're fine. Thank you for coming. Have a good day. We have an idea of mole fraction. So remember what mole fraction is? Mole fraction is a ratio. Yes. So it's simply a ratio. When we have a number here, if it's right smack dab in the middle, we're saying that half of our particular solution or whatever, it could be gas or liquid, is the A substance and half of it's B. So right in the middle we have this 0.5 number for both. But if we go this direction, let's say we're increasing A, which means it would actually be decreasing B, and the opposite for the other way. If we start going this way, we now have more A than B until eventually we get to the spot right here where now there is absolutely 0 of B and only A left. Does that make sense? Then the opposite would be true going this way. There's only B on this side. So let's say that this, our substance A, is pretty volatile. What does volatile mean? The volatility. It what? Evaporates quickly. Okay, so let's think about why for a moment. How come it evaporates quickly?
The intermolecular forces are really weak.
Yes. So you can think of it as, once again, thinking of that idea of, I guess, the door being open and people leaving. We could say it's a really big door. I don't know, like people can leave really easy.
Like two polar things, so it's like easy, or would that mean that it's?
No, it would actually mean the bonds just between them are weak. So if something was really polar, then it would probably hold on to itself really well. Like water, for instance.
Right.
I mean, water
So
evaporates, but
non-polar with a polar would probably be weak. What would be weak?
yeah. In terms of this, when we say A by itself is volatile, we're just talking about one molecule,
one.
Well, not necessarily two things combined, right? The A and the B would then be combined, which we'll talk about in a sec.
Okay.
So don't worry, you're good. So we have this idea that, let's say we'll use something like, I don't know, gasoline. Gasoline's pretty volatile. You can smell it really easily. So then it would be some sort of octane or some kind, I don't know. So I'm just going to make it up. So then we would say, let's say it has this pressure up here by itself. But let's say B isn't as volatile. Let's say it's like water. Water then, let's say, has a less pressure. So this up here, the sides represents pressure. These are pressure. So over here we have a higher pressure, but over here, when we have B by itself, water, for instance, it has a lower vapor pressure. But what if in our octane we start adding water to it? What's going to start happening to its vapor pressure?
Or wait,
It would
Will
go
it-
down
How come it will go down, and how come it won't go up?
right.
because you're adding a non-volatile substance.
Well, it is volatile, but not as volatile.
Yes.
Right. So then no matter what, it'll make its volatility go down. What were you going to say?
So
Something?
if we were to add octane to water, it would make water's volatility go up.
Yes.
Okay.
Hence, we have this line now that represents the overall pressure. So this is the overall pressure. Overall pressure. So we have the overall pressure, and that's even over here, right? Overall pressure. So then, as we're adding water to octane, the overall pressure goes down. But as we add octane to water, it goes up. And then we have the two opposite other lines. We have here octane. Let's say we have, over here we have 0 of water, all of octane. And over here we have 0 of water, but now we have only water here. So these lines just simply represent, okay, when we have this much water, or when we have only water left, or per se only water in there, this little line will go all the way here to the pressure, overall pressure. But as we then increase the amount of of octane, so you see now water level is going down, but octane is going up. You can see how eventually, you can, this is kind of weird, sorry, I'm being kind of funky. These lines represent how much of mole fraction there is of each individual one. Here we have only water, and we have octane at 0. As we add more octane, the mole fraction of water goes down, the mole fraction of octane goes up. And let's say we add octane all the way until, well, let's just say we had zero water and only octane. So now we have 0 water here and only octane. So that's what those two lines mean.
Okay.